Welcome to ICP 8. In this ICP, I'm going to concentrate on variational encoders. Again, in this ICP, I will follow the code that was provided in the classroom, but I will make some extensions to that uh, to put a perspective on the basic principles of variational encoders. So let's do a brief introduction. Um, First of all, an autoencoder is a neural network that is uh, that reconstructs its input. The main purpose of autoencoders is learning in an unsupervised way. For example, if we use autoencoder module to an input image, then it first encodes that image and then compress it, and in the next phase, a decoder is implemented so that uh, it can reconstruct the input. So combining encoders and decoders, and in between those encoders and decoders, we have the code, the compressed representation of the input images. So the whole system, the whole constitutes an autoencoder module. Autoencoders can be trained end to end or gradually layer by layer. In the case when we do it layer by layer, they are stacked together, which leads to a deeper encoder. That's what we are going to show today. Now, we are going to deal with convolutional encoders. The encoders compress the input into a lower dimensional code and then reconstructs the output from this representation. So on the top of the existing convolutional layers that was discussed in the classroom, I will introduce three additional convolutional layers that will allow our code to do a hierarchical decomposition of the input. So let's discuss the code. Let's start from here. So first, first thing first, let's import the libraries and then we uh, load the data, MNIST dataset. Um, and if we look at the data, let's see what do we have in the data. We have basically input train, we have training set and test sets in the data. And if we print the shapes, they look like this: 60,000 training data set, 10,000 test data set. But as pointed out during the class, there may be some memory issue with the free version of the Colab. So what I did is that I chose a subset of the data uh, from the train and the test set. So I have used 20,000 train data and 2,000 test data. So with those, I basically printed first 10 images in the data, and they look like this. There are, there are more images. Yeah, those are these images. So as a next task, we specify the data and the model configuration here. You can note that I have used a batch size of 50, number of epochs as 50, um, the batch size of 128, number of epochs as 50. Note that we can use more epochs, but in this exercise, our focus is the model, not the epoch. The encoder and decoder model, adding the additional layers to that. So I am now assuming that 50 epochs are good enough. following the suggestions in the classroom, and a validation split of 0.2. Uh, so next, let's there are I mean there are code segment for reshaping the data, and finally our input shape has this is our input shape. So here comes the most important part. Uh, that's the definition of the encoder. We have added, we already had three, two encoders, but we have added three additional conv2D layers with number of filters 32, 64, and 128. These are those filters. So we already had these two. I have added these three. The introduction, why, what help will these layers do? The question. So the answer is the introduction of more convolutional layers benefit our encoding module because with more hidden layers, the autoencoders can learn more complex coding. With more number of layers, we have also increased the number of filters. So it's just not adding more layers, we have increased the number of filters 32, 64, 128. We are gradually increasing those. As we move forward in the layers, the patterns become more complex, hence larger combinations of patterns to uh, capture. So we increase the filter size in the subsequent layers to capture as many combinations as possible. So adding more layer will make our analysis more granular, more hopefully more accurate, uh, and also we increase number of filters uh, as we add more layers to explore more basically. Also, you can also note that we have decreased the kernel size hyperparameter. The kernel size represents the number of pixels in height and width to capture more features of the images. The number of strides, the third variable, this one, they are down from 2 to 1. Um, a stride of 1 indicates that it slides pixel by pixel. So basically, adding more layers are justifiable from the point of view that we can capture more and more features in the input pictures so that when we reconstruct, we will be able to utilize those features and have a more accurate representation of the inputs. So we can see the snapshot of the model here. Next, let's work on the decoder module, the decoding component. And basically, we have used conv2D transpose packages, the tools basically at this with the same um, iteration as we, I mean, not the same iteration, but in the reversed same iteration as we apply conv2D um, encoders. So these are the decoders. Transpose function is used for decoding the response. Uh, and we use the same set of hyperparameters for each of these con2D transpose layers. These convolutions, which essentially compute the matrix transpose of a regular conventional layer, swapping the effect of the forward and backward bias as a result. So if we uh, so so basically this is our decoder, and if we do a summary, it looks like this for the following. Let me run the full code so we will know exactly whatever is going on. So here, so I'm repeating whatever I've done. So this is the first 10 images I'm decoding. Then I print, uh, then I do the data and model configuration. I reshape the data, just printing the input to the encoder. It's just a revision of whatever I've said so far. So this is the encoding operation, the conv2d layers, adding these layers. So getting the shape, defining the functions and lambda. Um, this is the encoder model summary. Then we define the decoders, and finally um, this is the snapshot of the decoder. So that's what that's where we are. Finally, we have to wire this encoder and decoder together. That stands for the variational autoencoder, right? So the variational autoencoders are composed here. So we wire them together, and this is our summary model. So input, we are basically, this is the sketch of the input versus output. So we passed this as input, we are reconstructing this as output with these many parameters as a free as the uh, fitting artifacts. So we can run this process of fitting. So we compiled it using the Adam optimizer and a loss function defined as binary cross entropy. When we run it for 100, 50 epochs, we can see the qualitatively what is the quality of fitting. So you can see the quality of fitting as a function of the loss. I mean, y-axis is loss and x-axis is the epoch, number of epoch, and you can see the blue line is the train and the orange line is the test. So you can see that with increasing epoch, we have a satisfactory loss performance, loss estimation, and you can see the loss is reduced with the number of epochs. Hence, that's number of epochs is quite justifiable from this picture. So let's go to the result of visualization as the next step. Uh, Basically, visualizing inputs are mapped into the latent space, are simply taking some input data, feeding it to the encoder, taking the mean values mu for the predictions and plotting them in a scatter plot. So visualization samples from the latent space is done in the following steps. First, we create a figure um, filled with zeros as well as linear space around mu equals 0, sigma equals 1. We can iterate over, and then we take a sample from the grid and feed it to the decoder. We then replace the zeros in our figure with the output, actual output, and finally plot the entire figure um, on the screen. This includes reshaping one-dimensional inputs if necessary. So uh, basically you can see this is the um, this is the scatter plot, and this shows the ultimate output uh, as a function, as a result of our autoencoder process. So from this exercise, I have learned uh, how to create a framework for autoencoders. Um, we have used the neural network convolutional neural network, and specifically in the Keras in the Keras framework, we have used Conv2D the layers in for reconstructing the images. The 2D because we have used two-dimensional layers. If we use three-dimensional pictures for as inputs, then we would have used Conv3D and so on. So that's about it, and I'll be sending out. I will be populating the GitHub repository with all the codes reports for more understanding. Thank you.